Now let's talk about azimuth distortions. We're going to look at a situation on the fourth quadrant. So let's suppose that what we have here are 2 points A and B. These points on the reference ellipsoid. We measured the azimuth alpha. Okay, so the azimuth is, of course, with respect to the meridian. If the azimuth from A to B is the meridian that contains point A. Okay, and now a few elements are important here. We have to realize that these distances, the distance between the 2 points, this is the distance on the reference ellipsoid. This is geodesic. The shortest distance between the 2 points is projected as a curved line. And this curved line is convex towards a reference meridian. So we have this reference meridian here, can be Greenwich, can be a meridian that we choose for convenience or following specifications. And here we have the equator. So that's why we then are forming these first quadrant, second quadrant, third quadrant, fourth quadrant. We'll talk about these conditions here. Gamma will have different signs, and gamma is the meridian convergence. So anyway, what we have first is we have to look at this is the line. This curved line represents the geodesic. It is projected on the mapping plane. So we call these the projected geodesic. Okay, so the distance between A and B will be S. SE. Okay. SE. What we have here, the other quantity, is the meridian that contains point A, which is also curved with respect to the reference meridian. Okay, so we can call this here the projected meridian of point A. The direction, of course, is counted from the tangent to the shortest distance. We just point, and the direction is the shortest distance. It's being projected as a curved line here. So this is the geodetic or the ellipsoidal azimuth. This guy here, alpha, is represented without any distortion. This is conformal map projection. The problem is that we want to make computations using grid elements. We are interested in the grid azimuth. And what is the grid azimuth? The grid azimuth is going to be the azimuth formed from the direction to the grid north and the direction between points A and B as a straight line, the shortest distance on the mapping plane. Okay, we want this angle T here. We don't want the angle we have the azimuth with respect to the so-called true north. The true north, strong and free. So, to establish the relationship between T and alpha, we need a few other terms. So one term we need is the meridian convergence. The meridian convergence will tell us how much the direction of the grid north and the true north vary, meridian convergence. Okay. The other angle is the T minus T correction. Okay, this is the arc-to-chord correction. T minus T because it is capital T minus lowercase t. Lowercase t is the grid azimuth. What is capital T? Let me get a different color here. Capital T is the grid azimuth of the projected geodesic. Okay? So now with all these elements, we can write down the expression here for alpha. So for T, grid azimuth equals to alpha, okay, plus gamma, plus T minus T. Okay, so this is, we are getting this figure here geometrically. Next, we're going to discuss a equation that is going to be general, because gamma and T minus T will be computed from equations, and they are going to come with either positive or negative, so we need to have a general way to express, to compute the grid azimuth. Now let's talk about the central meridian. The meridian convergence. Again, we have a central meridian. We have the equator. Okay, the central meridian can be anything, can be Greenwich, can be a reference meridian. We're going to see in UTM, can be the central meridian of a zone. In the first quadrant and the third quadrant, gamma is positive. This meridian convergence is positive. In the second quadrant and in the fourth quadrant, the meridian convergence is negative. Along the equator, gamma equals to 0. Along the central meridian, gamma equals to 0. Another important thing is that the value of the meridian convergence varies with latitude. So if we have a point on the equator, this is the direction, the tangent to the projected meridian. This is the true north. True north, it coincides with the grid north. Okay, we may have a point in here. So this is the grid north, of course, points like that, the grid north. And here we have the tangent, which represents the true north. So this is gamma. If you are here, we're going to have again the grid north, and the tangent is here, so this is gamma. Okay, so as we move to the north or to the south, the value along the same meridian, the same projected meridian, the value of the meridian convergence grows. How to compute the meridian convergence? We can do that by means of these, the evaluation of these derivatives. We have here a equation as a function of the isometric latitude, and we have here another equation as a function of the geodetic longitude. Now let's look at a general expression for the grid azimuth. General expression for the computation of the grid azimuth as a function of the given ellipsoidal azimuth. So we look at the first quadrant. We have these 2 points A and B. We have here the projected geodesic, the direction of the true north, direction of the grid north. We have the this is the projected geodesic. Okay, it is curved. If this thing here is first quadrant, the meridian, the reference meridian is here, okay, and the equator is here. So something that I forgot to mention when I introduced this quantity here, the projected geodesic is always concave towards the reference meridian. The projected meridian is curved, okay, towards the reference meridian. So this is a general rule. It doesn't apply in Mercator, but it applies in all the others that we're going to study. So what we are given? We are given this guy here. Okay, the angle, this is the measured angle, the measured azimuth. Meridian convergence, we will compute. T minus C correction, we will compute. We're going to have expressions to compute that. Okay? T can be computed from the angle, the azimuth, the ellipsoidal azimuth, and the meridian convergence. If we need T, okay? We may not need T. But this is the T, this is the grid azimuth of the projected geodesic. So starting from the grid north, we go all the way to the projected geodesic. This is the tangent to the projected geodesic, because the angle is right here. What about the grid azimuth, the quantity that we are interested in ultimately? So T is going to be alpha E, this is the whole alpha E, minus gamma, minus T minus T. Okay? Here you go. This is general expression. We can always use this equation here. Okay? We use this equation, we compute gamma, we compute T minus T, it will come with the proper sign. So it doesn't matter the situation where we are, the first, second, third, or fourth quadrant, this expression here we will always hold, provided we are using gamma and T minus T, with the sign as given in their computations. What about directions? Directions and angles. So, the grid azimuth we have just seen, this is the expression. What if we're measuring a direction? So we're set up here, we are measuring direction from J to K. So the direction on the reference ellipsoid follows the projected geodesic. But on the reference, on the mapping plane, the direction has to follow the shortest distance, which is a straight line. So we have to correct by the t minus t correction. Okay, so the direction on the mapping plane equals to the direction on the reference ellipsoid. The ellipsoidal direction can be the projected direction, doesn't matter. It is the same because this is a conformal map plane. Minus t minus t. So where is it? T minus t is right here. T minus t of between j and k. Okay, if you wanted the direction on the mapping plane between j and I, it would be what? It would be the direction that was measured on the ellipsoid, which is the same as the projected. It's projected without deformation, distortion. Minus t minus t of point j and I. What about the angle? Well, the angle is obviously we are going to subtract both directions. So this is the angle that was measured, omega p projected between I, J, K, I, J, and K. This is the direction of the angle measured, plus t minus t ji. We have to add here, minus t minus t jk. So this angle here is this one plus this minus that. Okay? The arc-to-chord correction has this general expression. It's going to be derived for each one of the conformal projections based on the curvature of the projected geodesic. So the azimuth direction angle corrections we have seen already. The mean scale factor, we discussed about the point scale factor, but we are dealing with actual distances. So distance between 2 points I and j, we compute the scale factor, the point scale factor at each one of these 2 points and compute the mean scale factor. And then we apply the mean scale factor on the ellipsoidal distance, and you get the mapping distance. Now, this mapping distance, there is a slight difference between the this mapping distance and the grid distance. Okay, it can be evaluated also as a function of the curvature of the projected geodesic. This is very small. In most well, this goes to 0 in most our cases. Therefore, we can basically consider that Sm equals to L. So we are going to use, well, we are going to use either Sm or L in our equations. Okay, they'll be the same. Finally, we arrive at the expressions for the direct and inverse problems. And you can see that all the effort paid off, because ultimately we're dealing now with very simple trigonometric expressions that we are familiar with. So we know that the angle T, which we are using here, this is the azimuth, the grid azimuth, it comes from the ellipsoidal azimuth, applying a few corrections. The grid distance will come from the ellipsoidal distance, applied the scale factor. So there is some data treatment that is required, but then the computation on the conformal mapping plane is simple. For the inverse problem, if we know the grid coordinates of the 2 points, we can compute the grid distance, and we can also compute the grid azimuth. So next, we're going to look at individual projections, conformal projections, looking at the equations and their characteristics. Okay, see you later.